Thank you for joining me today. My name is Yesica Salas. I am currently studying Master in Science Statistics. In this opportunity, I am going to talk about dimensionality reduction. I am going to divide this talk into three parts. First of all, I'll discuss an introduction and motivation about dimensionality reduction. What is dimensionality reduction? Why is important compressed data? Then I will mention the principles method for that. Secondly, I will talk about one special method about dimensionality reduction. It is PCA. What is PCA? How does it work? The steps for performing PCA and how can we choose the number of principal components. Finally, we will execute this method on Python. Let's start. Suppose we need to classify women in diabetic or not diabetic. This can involve a large number of features, such as pregnancy, blood pressure, age, level of glucose, level of insulin, or diabetes pedigree function, and so on. Sometimes, most of these features are correlated and hence redundant. What can we do for improve our classifier? What is dimensionality reduction? Dimensionality reduction is the procedure of reducing the number of random variables under some considerations, with the goal of obtaining a set of principal variables which capture the highest possible variance and information about the original dataset. If we have a large dataset with 50 variables or more and we need to train a learning algorithm, then we probably have to compress the data. The higher the number of features, the harder it gets to visualize the training set and then work on it. Dimensionality reduction aims are two. The first one is called feature selection. The goal is to choose the P less to K most important features and to get a smaller subset of the original set of features. For example, in the problem about classifier women in diabetic or not diabetic, we can choose the most important features for training the model, like blood pressure or level of glucose or level of insulin. The second is called feature extraction. Project the original dimension to new P less to K dimension. We transform the points from RP RK to RP with P less to K. That is to say, reducing the dimension space to lower dimension space. Why compress the data? Compressing data is very important because it allows us to use less memory in the computer or less space on the disk. It allows us speed up learning algorithm or use other simpler algorithms. Quit the features which are not relevant in our problem. If we compressing the data, we can visualize data in 2D or 3D. However, dimensionality reduction has disadvantage. We lost data of the original dataset. We can find considerables linear correlations between variables. PCA can fail sometimes where mean and covariance are not enough. We don't know how many principal components we can select exactly. And then the quantify of principal components is subjective. We can select there are many methods about dimensionality reduction. The principal of these are PCA, principal component analysis, linear discriminant analysis, LDA, quadratic discriminant analysis, QGA, regularized discriminant analysis, RGA, multidimensional scaling, MDS. What is PCA? PCA is a common statistical tool for reducing the dimension of a data into specifier smaller dimension. It is considered an unsupervised learning algorithm because it doesn't require a labeled dataset. It allows us to quantify the variability of the data. PCA helps to visualize better the high dimensional data. In this graphic, we can see different points of our dataset. If we plot this line in this direction, we consider the projection of the points over the line. Now we have a new dataset projected. For PCA, it conveniently turns out when determining the principal components, the maximal variance of the project data minimizes the square of Euclidean distance between data and their projection. Now I have a challenge for you. What plot is more convenient for the principal components? Let's think in it. Okay, if we plot the principal component, the first principal component in this direction in the first graphic and in this direction in the second graphic, we have the highest distance between the data and their projection. In contrast, the third graphic where we have the minimal distance between the data and the projection. How does it work? PCA transforms variables into a new set of variables which are a linear combination of the original data. PCA is an orthogonal of linear transformation that represents data in a new coordinate system. The new variables are known as principal components. Initially, there are the same numbers of features like principal components, and these mustn't be correlated. The principal components aims to capture as much information as possible with the high spline variance. Thus, the first component has the highest variance, followed by second, third, and so on. In this graphic, we can visualize the original data set in 3 dimensions. Then, if we apply PCA, we plot the first principal component in this direction. Next, the second principal component in this direction, which is orthogonal to the first principal component. Now we can visualize the data in 2 dimensions. Okay, mathematical formulation. Let x equal to x1, x2, x3 until xk be a n times k data matrix with n observation and k features. The covariance matrix is given by sigma equal to the expected value of the product of x minus expected value of x transpose and x minus expected value of x. If we have the expected value equal to 0, we can simplify the covariance of x like 1 on n minus 1 by x transpose times x. It is a matrix of k times k. Let P1 the first principal component. B1 is equal to theta 1 by x1 plus theta 1 by x2 plus so on theta 1k by xk. It is a linear combination of the original data features. The projection of x on the direction of b is called c. C is equal to x transposed by b. Find b such that the variance of c is maximized. Maximizing the variance is equivalent to minimize the Euclidean sum of squares projected error. The variance of b transposed by x is given by the expected value of the square of b transpose x minus b transpose mu. Here we open the square factor and here we factorize b and b transpose. Then we apply the expected value, and finally we obtain this equation. Note, the variance of x is given by sigma. The first principal component. In PCA, B1 is chosen such that it maximizes the variance of C, subject to this constraint. Thus, our objective is to solve the maximal of this equation. Now, it is an optimization problem. Then we use the Lagrange multiplier. We solve this problem, derivation from B1, this equation. Now we have 2 sigma B1 minus 2 lambda 1 B1 equal to 0. The solution of this is given by sigma B1 equal to lambda 1 B1. Note, B1 is an eigenvector of sigma. If we replace this value in the variance of C, we have the variance of C is equal to lambda 1. The first principal component, B1, is the eigenvector of sigma, which corresponds to the largest eigenvalue, lambda 1. Now, we determine the second principal component. We maximizing the variance of C, subject to these two constraints. This one is because B2 is an unitary vector, and this one is because B2 is orthogonal to B1, and then their product is equal to 0. We repeat the same procedure in the previous principal component. Deriving this equation, we obtain 2 B1 transpose sigma B2 minus 2 lambda 2 B1 transpose B2 minus delta B1 transpose B1 equal to 0. Note, this factor is equal to 0 and this factor is equal to 1 because B1 is an unitary vector too. In the other way, 2B1 transpose sigma B2 is equal to 2B2 transpose sigma B1 equal to 0. If it is 0 and it is 0, we have delta equal to 0, and hence sigma B2 minus lambda 2 B2 is equal to 0. Finally, we obtain sigma B2 is equal to lambda 2 B2. Note that B2 is another eigenvector of sigma. We replace this value in the variance of C. The variance of C is equal to lambda 2. The second principal component, B2, is the eigenvector of sigma, which corresponds to the second largest eigenvalue, lambda 2. Proceeding onwards. Now we have the eigenvalue lambda 1 and the corresponding vector b1 of sigma. The eigenvalue lambda 2 less or equal to lambda 1 and their corresponding vector b2. If we carry on until the p principal component, we have the eigenvalue lambda p less or equal to lambda p minus 1 and the corresponding eigenvector bp. Steps for performing PCA. Before we start performing the PCA in our data set, we have to normalize the data. This is the step 0. We have to apply this transformation over the original data set. Step 1. Find the matrix of covariance sigma. Step 2. For sigma, in the step 1, find all eigenvalues and their corresponding eigenvector and sort this. So, the B1 is the first principal component, B2 is the second principal component, and so on. Step 3. We construct a metric with the first P principal component. P reduced is given by B1, B2 until BP. Note that P reduced is a matrix of K by P dimensions. We will transform the original dataset into a matrix of n by p dimensions, where n is the number of observations and p is the number of features. Step 4. Finally, to get our resulting data in p dimensions, compute c equal to x by p reduced. Now, c is a n by p data matrix that it is the result of PCA. Choosing K, number of principal components. If our objective is visualize the data, then picking the first two or the first three principal components that makes sense. Typically, choose K to be smallest value so that 99% of variance is retained as below. 1 on m by the sum from I equal to 1 to m of the square of the Euclidean distance between each observation and their projection. Onto 1 on m by the sum from I equal to 1 to m of the square of the norm for each observation is less or equal to 0.01. For k given, we have this equation. Adding up 1 to both sides, we have to pick the smallest value of k, for which the sum from I equal to 1 to k of Sii over the sum from I equal to 1 to n of Sii, higher or equal to 0.99. In the practice, we will probably want to choose keeping the first P principal components, such that the total proportion of the splaying variance is above 85%. This plot is a graphic of the proportion splaying variance versus the principal component. Here we can see the first two principal components retain the 85% the variance over the original dataset, and hence we choose k equal to 2. The last option about choosing k is graph the plot of proportion splaying variance versus k and stop at elbow. The elbow method will be analogous to the elbow human. If we reach out our arm, we can look at this part of the graphic looks like the human arm. The elbow in the graphic looks like the elbow human. Here we can see the best option of k equal to 4. Let's to execute this method on Python. To execute PCA in Python, simply import PCA from sklearn library. Let's do performance this tool learned for recognition of handwriting digits dataset. This notebook is an important source about PCA because I follow this for my talk. They explain PCA and then they propose an implementation for this. They use a database about women test positive for diabetes. They apply PCA to visualize the data in 2D and 3D space. It is the data in 2D and it is the data in 3D. This other notebook is an example about PCA for recognition of handwriting digits data. Here they load a database of digits. Here they import PCA from sklearn. And here they feed PCA. If you change this value of M, you can choose the number of principal components about this plot. The first task for you is change this value of M and choose the better number of principal components. Finally, they plot the data into 2-dimension and 3-dimension. Here 2-dimension, here 3-dimension. The second task for you is run this code about PCA for visualize the previous database of women tested positive for diabetes.